Assalamualaikum. Hi. So today we're going to look at the derivation of EMF under the subtopic 5.2 induced EMF. So as we know that EMF is induced, okay, that EMF is induced when there is flux change in the coil, or mathematically based on what Faraday and also Lenz has concluded that EMF is equals to negative d flux over dt, where Faraday stated that EMF yang kita akan induce itu directly proportional to the rate change of the magnetic flux. Okay, so every time ada change in the magnetic flux, you can induce EMF. Dan this EMF yang kita induce ini, you can increase the value dia when you use a stronger magnet. Bila kita use stronger magnet, the magnetic flux akan increase. How does stronger magnet related to magnetic flux increase adalah, kita kena relate balik dengan equation ini, iaitu flux is equals to BA cos theta. When you use a stronger magnet, it indicates that the magnetic field, iaitu B, magnetic field strength ini lebih besar. Bila lebih besar, B besar, your flux is also going to increase lah kan. Okay, so bila flux increase, rate of change kita jadi besar dekat sini. So EMF yang kita akan dapat pun increase dekat sini. Same goes to when you push a magnet faster into a coil, the speed of the magnet is going to increase. Okay, and then when you increase the area becomes greater. Kita ada A yang lebih besar, flux pun akan increase. Same goes to when you have the more number of turns in a particular coil, you are going to induce more EMF. Okay, so now we are going to look at the cases, how the equation going to look like when you change the term in the equation. Okay, so let's say kita ada coil of N turns placed in a changing magnetic field. Okay, changing magnetic field, what is going to happen to your EMF adalah, kita tahu EMF is equals to negative N d flux over dt, where your flux adalah BA cos theta. Okay, so what is going to happen dalam case ini adalah dia cakap changing magnetic field. Maksudnya magnetic field kita sahaja akan berubah. Let's say you have magnetic field sebanyak 5 Tesla dekat sini. Okay, you first initially place your coil dekat 5 Tesla ni, awak letak dekat sini, and then lepas tu awak buat apa? You are going to increase the magnetic field. Kita tambah magnetic field, kita jadikan dia lebih kuat. Let's say now we are going to use 10 Tesla dekat sini. Kita guna coil yang sama, kita letak. Okay, so you're going to have greater magnetic field dekat sini. Your B changes. Apa yang berubah adalah B berubah. Okay, so this equation now becomes negative N. A tak ubah, cos theta tak ubah. So you do not do anything with them. You bring them to forward. Dia akan jadi dB over dt. Where your dB over dt ini adalah B final kamu minus B initial bahagi dengan the duration of your time itu. Okay, so same goes to when you have N turn is placed in a uniform magnetic field but changing in the coil's area. Okay, so apa yang akan jadi adalah sekarang kita akan ubah area. You still use the same magnetic field. Okay, kita ada magnetic field yang sama, katakan 5 Tesla dekat sini. Cuma initially you have area of circle ini atau coil ini sebanyak katakan 2 meter square, and then suddenly you increase the area. So bila awak increase the area, what is going to happen adalah you're going to have more B that crosses this cross sectional area. Area kita pula yang berubah. So bila area berubah dekat sini, this same equation ini kita akan tulis, akan jadi negative N, B tak ubah, cos theta tak ubah, dA over dt, as your area is the one who's going to change. Area kita akan berubah dekat sini. Same goes to when you change the angle between the plane of the coil and also magnetic field. Bila kita tukar angle, equation yang sama ini kita akan tulis such that negative N BA, sebab kita tak tukar magnetic field dia, kita tak tukar area dia, it's just that the cos changes. So bila kita nak tulis, kita akan tulis cos theta final minus cos theta initial bahagi dengan dt dekat sini. Okay, so this becomes your equation. So however, you don't have to memorize all these 3 equation. Awak tak payah pun nak hafal semua 3-3 ni. Okay, you can simply derive daripada yang ini. Yang penting kita faham flux adalah BA cos theta. You identify siapa yang akan berubah dekat sini. Okay, next we are going to look at the derivation of induced EMF involving conductors in a uniform magnetic field. Okay, so what are we going to have is a straight conductor moving in a uniform magnetic field, and we're going to see how are we going to induce the EMF for this case. Okay, consider we have a straight conductor PQ of length L is moved perpendicular with the velocity V across a uniform magnetic field as shown in the figure below. Okay, so what we have here is our external magnetic field. This is our B here, and the B is used cross to indicate the direction, such as kita punya B external ini, direction dia adalah into the page. Okay, so the cross here is into the page, and then we have our conductor here, PQ. However, initially it was here. Okay, initially it was here. It has a length of L. We moved it with a speed of V. Okay, kita gerakkan dengan kelajuan V ini ke kanan, and this is the new location here. So let's say kedudukan asal ni kita panggil dia P prime, Q prime, and then you moved it with the speed V across a distance X here. So when the conductor moves through a distance X, so this is the distance that you're going to move through, in time T, the area swept out by the conductor is given by A is equals to Lx. Okay, so what is going to happen adalah initially this was the length of the conductor, and then this particular length moved across a distance X to be in this new position. So basically area yang di cover oleh this conductor adalah the length multiplied by the distance moved. Okay, so the area here becomes L multiplied with X. Since the motion of the conductor is perpendicular to the magnetic field B, okay, kita bergerakkan velocity dia ke kanan, and the B here is into the page. They are perpendicular to each other. Hence, magnetic flux cutting by the conductor is given by, kita tahu flux is equals to BA cos theta. Since kita punya flux magnetic field is perpendicular to the motion dekat sini, so kita dapat theta kita as 0. Theta becomes 0, so cos 0 gives you 1 here, and then your flux here akan sama dengan BA. Okay, BA darab 1, A pula sama dengan BL darab dengan X. You substitute this area here, so you will end up with equation BLX. Okay, your flux here become BLX. Okay, ini adalah flux kita. Alright, so according to Faraday's law, the EMF is induced by the conductor and its magnitude is given by, because you are swiping it, so kita akan ada EMF kita sama dengan D flux over DT dekat sini. Flux kamu adalah BLX, so you substitute that into, so you'll get BL dx over DT. Okay, magnetic field did not change, the length of the conductor tidak berubah. Jarak yang kita swipe ini yang tengah berubah. Okay, you are slowly increasing the distance. Daripada tak ada jarak kita swipe, sekarang kita ada jarak, so your distance here changes, dx over dt. Dx over dt is V, velocity. So in general, the magnitude of the induced EMF in the straight conductor is given by EMF is equals to BL, kita tak kacau, V jadi, dx over dt jadi V sin theta. Theta dekat sini adalah angle antara V dan juga B. So every time you have case of conductor moving in a uniform magnetic field, kita boleh induce EMF such that the magnitude of the EMF akan jadi BLV sin theta. B adalah the external magnetic field kita. L dekat sini adalah the length of the conductor. V adalah kelajuan kita gerakkan dia. Theta is the angle between V and also the B. Okay, so lepas kita dapat induce EMF ini, kita boleh juga dapatkan current yang kita akan induce across that conductor. Kita boleh dapatkan I induce menggunakan Ohm's law, iaitu V is equals to IR. V dekat sini adalah EMF kita. So kita rearrange, kita akan dapat induce EMF over resistance. You can get the induced current. So kita boleh dapatlah nilai I yang kita akan induce. However, you must know the direction of induced current and also the direction of induced EMF in this conductor. Kita kena tahu dia punya direction. So kita akan how do we deduce adalah menggunakan, so as you can see, this type of induced EMF is known as motional induced EMF. You must have motion in order to have area covered so that you can induce the EMF dekat sini. The direction of the induced current or induced EMF in the straight conductor can be determined using right hand rule. So kita akan menggunakan kaedah right hand rule kita untuk menentukan direction of EMF dan juga current kita dekat sini. So magnetic flux increases as the area swept by the conductor increase. Okay, flux kita, dia kata flux akan increase bila area swept by the conductor increase. Kenapa? Sebab flux is equals to BA cos theta. So when the area increase, flux akan increase juga. Thus, area increases, B is induced. Okay, thus area increases, B akan being induced. The B induced ini directed out of the page. Okay, macam mana kita nak tahu B induced kita directed out of the page adalah kita akan kembali kepada table kita, iaitu you have originally your flux was BA cos theta. Okay, and then kita tahu kita akan ada 3 case. Either your flux ni increase, decrease ataupun sama. Okay, kalau dia increase apa jadi? Kalau dia sama apa jadi? Kalau dia decrease apa jadi? So when you increase the change in the flux, maksudnya flux kita berubah dari segi peningkatan, what is going to happen adalah you're going to induce magnetic field. Magnetic field yang kita induce ini akan opposite to B external kita. It's going to be opposite to B external. However, if it remains the same, B ini kita takkan induce. No B induce. Sama dengan kosong. Kita takkan induce any magnetic field dekat sini. And then, bila decrease pula, B induce kita same direction dengan B external. Same direction dengan B external kita. Alright. And then, using this direction of B induced yang kita dapat deduce tu, kita akan determine the direction of current dan juga EMF. So, macam mana kita nak tengok dekat sini adalah, kita kena first identify how the flux changes. So, dalam case ni kita cakap area dia akan berubah. Okay, macam mana kita nak cakap area dia akan berubah adalah, initially dia tak ada area yang dia cover. After that, it is going to move across a certain distance. So, dia akan swipe and then produce a new area dekat sini. Betul tak? Okay. Untuk memudahkan, Miss akan cadang, this is my style saya akan cadang, kita ambil kita punya external field sebagai area kita. Where does your external field start? Selalu kita ambil bahagian kiri inilah, left of your page. So this is where your external field starts. Okay, and this is where your conductor is sitting, P prime dengan Q prime. This is the initial area. Okay, ini adalah initial area kita. Okay, kita assume, walaupun kita tak nampak area ni, tapi kita assume kita start daripada ini adalah area asal kita, from where your field line started to where your conductor is located. Okay, lepas tu kita gerakkan dia ke kanan. You are moving it to the right. So the conductor now has seated in a new position, which gives you a new area. So kita ada area yang baru, iaitu area daripada initial point of the external field sampailah di mana conductor itu duduk. Ini adalah area baru kita. So area final kita pula, the blue color one. Okay, ini adalah area final kita. Okay, however, area yang kita cover, area yang kita perubahan dalam area, delta A kita, your delta A is only this part sahaja. Ini sahaja delta A kamu. So dia meningkat sebanyak ni lah kan. This is how much it changes. This is how much it changes, which is the area yang kita cari dan kita masukkan dalam equation flux kita, betul? Alright. So, area yang kita cover ini is your delta A. Okay, so as you can see, your area increase. Area initial hanya bahagian sini saja. Area final adalah dari sini sampai ke sini, this whole area. So your area increase. Bila area increase, what is going to happen adalah your flux going to increase according to this equation. Bila flux increase, kita punya B induced opposite direction to B external. Okay, B external kita into the page, maka B induced kita akan opposite dengan dia, iaitu out of the page. Ini adalah B induced kita out of the page. Out of the page ini, let's say kita assume dia adalah dot dekat sini. Okay, so kita akan ada B induced jugalah at this particular point. So dot. Okay, akan ada banyak lah dot. Okay, ini semua indicate B external kamu. Alright, so now kita akan menggunakan right hand grip rule to identify the direction of I induced based on the direction of B induced. Okay, so sekarang what you do is you take your right hand. Okay, your thumb here indicate the B induced direction. Your fingers that is going to curl akan indicate the direction of I induced flow. Okay, apa yang kamu kena buat adalah kamu sekarang ambil tangan kamu letak di atas petak delta area, iaitu peningkatan area kamu tu kan, bahagian yang area setelah dia berubah itu, which is this part lah delta A kamu. Okay, dekat sini. Okay, kamu letak dekat bahagian sini sahaja. Kita letak dekat bahagian sini. Okay, you're going to place your fingers at this particular point. Okay, awak nak letak dekat sini. So, awak ambil tangan kamu letak dekat sini. Ini tangan kamu sekarang. Okay, dah letak tangan dekat situ. Kamu ambil thumb kamu, pastikan dia point out of the page. And then kamu akan nampak your fingers is going to curl in this direction. Fingers kamu akan pusing ke sini. Betul? Fingers akan pusing ke anti-clockwise direction. So, indirectly, this gives you the direction of your current flow. So, kamu akan ada current yang akan flow in the anti-clockwise direction. Daripada Q prime ke Q, Q ke P, P ke P prime, and then P prime ke Q prime. So, this is the direction of your I-induced flow, anti-clockwise direction. Okay, so kalau kamu tengok dia kata B induced directed out of the page to decrease back the magnetic field and the fingers curl shows anti-clockwise direction in the closed loop drawn. So ini adalah closed loop yang kita lukis, iaitu di antara kedudukan asal dia dengan kedudukan akhir dia, which was the delta A tadi tu. Okay, so you place your hand here, letak dekat bahagian sini sahaja. Okay, letak dekat bahagian sini. And then pastikan thumb kamu point out of the page. And then kamu curl your fingers. You're going to get the direction of your current adalah anti-clockwise. Therefore, the direction of the induced current from Q to P, iaitu sekarang kita kena faham area ini adalah area yang hanya kita nampak because we have imagined the area. The conductor initially dekat sini, sekarang dekat sini. So you have to say the direction of flow of the current in the conductor. Kita nak kena cakap direction of current flow itu dari segi di dalam conductor itu. Conductor sekarang duduk dekat sini. Okay, so look at your conductor. The current is going to flow upwards in the conductor, iaitu daripada point Q ke point P. Okay, so this is the direction of your induced current, iaitu induced current flow from Q to P ataupun upwards. Okay, dia naik ke atas. Okay, so when your current is flowing in that particular direction, therefore, kamu akan ada potential at P is higher than potential at Q. Potential dekat P ni lebih besar daripada potential dekat Q. So, this one has a higher potential. V kamu besar. Dekat sini V kamu lower. Dekat sini high potential, low potential. Because the current is flowing from Q to P. Dia akan flow daripada low potential to higher potential. Okay, so kita boleh guna this equation to get the induced EMF. Dan kita boleh dapatkan direction of induced current menggunakan kita punya right hand grip rule, menggunakan pemahaman area increase, flux increase, B induced opposite to B external. Okay, next we are going to look at induction of EMF in a rotating coil. Right? So suppose that coil has N turns and all the same areas A and rotates in a magnetic field with a constant angular velocity omega. Since it is rotating, so velocity dia dekat sini kita guna angular velocity. So let's say this is your rotating coil. Okay, made up of many turns and number of turns, and they all have the same area and rotates in a magnetic field. As you can see, this is your permanent magnet, North Pole and South Pole. So you're going to have magnetic field line dekat sini lah kan. This is your uniform magnetic field. The induced EMF in the coil with N turn is given as EMF is equals to negative N d flux over dt. Knowing that the values of B, N and A are constant and only the orientation of the coil theta changes with time. As you can see, B yang kita dapat dalam soalan ni adalah from the permanent bar magnet, dan bar magnet ini adalah bar magnet yang sama. So your B did not change, it is a constant. The number of turn pun tidak berubah. Area of the coil pun tidak berubah. What is changing here is the orientation of the coil theta, because you are rotating dia. Therefore, your EMF is equals to negative N d flux over dt can be written as negative N d BA cos omega t dt. Okey, selalu kita kata cos theta, betul tak? Theta ini adalah angular displacement in terms of rotating object. So, kita substitute dia dengan angular velocity darab dengan time. So, you're going to get EMF is equals to negative N BAD cos omega t over dt. Sebab apa yang tengah berubah adalah dia punya orientation, dia punya angle yang berubah. So, we are going to differentiate the term cos omega t dekat sini. So, the magnitude of EMF induced in a rotating coil is given as, bila kita differentiate d cos omega t over dt, what are you going to get is, you're going to, okay, so apa yang kita akan buat adalah omega kita bawa ke depan, differentiate cos, dapat negative sin omega t, and then you have negative nba. So, negative nba, and then negative cancel, so you end up with nba omega sin omega t. So, this is your magnitude. Alright, T dekat sini adalah masa. Okay, maximum EMF can be induced. Maximum EMF can be induced when your sin omega t is equals to 1. Bila sin omega t sama dengan 1, which means NBA omega sin omega t. So, kalau EMF maximum, it means that this whole thing has to be 1. So, kita dapat NBA omega sahaja. So, kalau dalam soalan dia kata maximum induced EMF for a rotating coil, NBA omega. Okay, so that's it for 5.2 derivation of induced EMF.